Good morning, everyone, and welcome once again to AP Calculus BC Live. Here we are again, just to prove to you that there is more than corn in Indiana. Yes, we have the greatest spectacle in racing, the Indy 500, which is going to be a little later this year. And although we're not the place where basketball was invented, we're said to be the place where it was perfected. But we also have the two nerdy guys that like to get up early in the morning and teach you guys AP Calculus. And that's what Brian and I are going to do today with our lesson, free response questions, putting it all together, taking these ideas that we've talked about over the last several days, several weeks, and throwing them together in these nice, cohesive free response questions so that we can better prepare you for what might lie ahead on your AP exam coming up here in just about a week and a half now. As always, we want to welcome you to download any of the materials that will go with any of our videos, and you can do that in the description below each particular video. And like every other morning, I'm joined with my good friend, my fellow Hoosier, my calculus partner in crime, Mr. Brian Passwater. Brian, I I hear that there's some really cool things going on next week. That's the rumor circulating all over town, all over the United States, through Canada, through Mexico, all across the world, that we're going to be talking about some potential t-shirt giveaways. And rumor has it that there's a mock-up for this t-shirt, and the fact that we have the amazing Dr. Stephen Kokoska coming on to talk to our students and teachers. Is that right? Is that what's going on?
Tony, I'm excited about today's lesson, but next week is going to be incredible. So yes, to hit it on the head, I think you did a good job of that. So three quick things, right, before we get into today's FRQs. Next week, we mentioned this yesterday, but our good friend, Dr. Steve Kokoska, who's a former chief reader, that is the top person, right, in charge of the scoring and the overseeing of the grading of the exams, will be here with us on Tuesday live. He'll be here live. And so if you have questions like, man, I always wanted to know this about the reading, or I want to know about this about the exam, or just different things, and want someone's input who's written exam questions, who's been in charge of grading the exam, a brilliant person, but incredibly humble, extremely knowledgeable, join us. You have an opportunity during our live session to tweet out at Steve and ask him questions. So make sure you're here for that for Tuesday. Also next week, every day next week, we're going to be getting you ready, not just for the content of the exam like we've been doing, but really walking through a part of our lesson every day will include all of the logistics about the testing. We'll be talking about what you're going to be doing on exam day, the checklist, making sure you have everything you need, knowing how to get your testing ticket, how to log into the system, what to check for in advance, how to practice the whole uploading. I know sometimes students are a little bit nervous about uploading their answers, and how, if they want to type on their computer, what would that look like, and how do you save a file? We'll be doing that every single day next week, a little bit each day, and also practicing timed FRQs like the system will do. So kids will get a really good experience with that as well. And we're going to give you a little bit of homework this weekend, because next week we're going to be using the College Board's put out this demo so our students can practice uploading their responses just to make sure it works, right? So it's kind of like a generic demo for all AP courses. So you know, for all your AP classes, just, hey, how do you upload a text file? How do you upload a picture from your phone? And you'll have a chance to do that. You'll be able to see how the timer is going to look on your screen, so they can play around with different devices to figure out what's going to be the best one for them. And also the demo is a great opportunity because it's going to let you know whether you can access the test on test day. If the demo site works, then you know that you can access the test when it comes down to it. If you're not getting the demo to work, then we have to troubleshoot. Maybe your internet browser is not compatible. You've got an add-on to your thing that we have to fix. And so we'll deal with that all next week. We'll be here every step of the way, answering your questions too, you know, that we can help you if you have questions. So, but perhaps I think the biggest and most exciting thing, Tony, is the t-shirt giveaway. We mentioned we're going to have a t-shirt giveaway every day next week. If you're watching, we're going to have some criteria that you're going to meet. But starting next week, every day, you can win a free t-shirt, not just for you, but for you and your calculus teacher. We'll ship them right to you. And in honor of that, Tony, I thought it was okay with you. I want to share a little bit of a preview of the shirt. Are you okay with that? To do that without it being next week?
Let's take a look at it. Why not?
So I got a little special background. This is a part of it, right? Tony hasn't seen this yet. So I think his one comment to me was, I'm fine with the shirt giveaway. I just don't want my face on the shirt. So I cartoonized our faces, Tony, that we were unrecognizable. So no one will know That's us. So I think it's pretty well disguised, but the front is going to have this. Hey, you've been on the world tour of Tony and Brian's world tour, and the back is going to have all the dates. It's going to be pretty awesome shirt that we'll be giving away again every day next week. And Tony, speaking of shirts, it looks like you're wearing a little calculus shirt uh, today. What's going on with that?
Why, yes, I am. I think beginning today and through every day next week, I'll just rotate my little calculus wardrobe. I think this is shirt 16 out of 17. We have 17 designs, one every year since I started to do this way back in 2000, I think 2004. And yeah, this one's got the Friends motif going on. So yeah, we'll kind of commemorate our t-shirt giveaway. And I know that Brian has done the same, and I think he's going to start sporting some of his shirts to kind of get you in the mood. That's what we're going to do. We're going to get you in the mood to take this AP Calc exam. So yeah, sounds great. Sounds great. Hey, I'm going to go ahead and share with you the site that Brian talked about. And yes, this is a little additional part to your homework. It's really important. We want you to go to cb.org/AP demo and try this out, and not just once or twice, but try this out several times so that you get very proficient with the manner in which you want to take your AP exams, and not just so much with calculus, but with all of your other subjects. And we're not going to talk through it in detail today, but once you log in, you would go to this particular site. This screen would pop up, and you will not have your 8-character AP ID anytime soon. It's going to happen 2 days before you take the test. But as you can see, it asks you to type the word in practice. And once you do, you can then continue, and then it just prompts you to enter some other information, much like the actual site's going to do. And then once you start to do that, a little timer begins, and you can then enter this information. And then once you go through that phase, you can actually talk about, or read about, I should say, the various ways that you can uh, attach your work, take photos and attach, etc. So it's going to be a very valuable experience for you to play around with that. cb.org/AP demo. And of course, we'll go into a lot more detail with that with you next week. So as they say in France, without further ado, ooh, we got a little AP French there all of a sudden. Yeah, we're going to talk about some free response questions, and we're actually going to start up with problem 0. Not that problem 0 doesn't matter. Problem 0 probably has a little bit of a complex that he's called problem 0, but it's really kind of a little bit of a completion of what we were starting to talk about at the end of the broadcast yesterday. And we wanted to go into this idea of this particle motion that's all this nice, wonderful, cohesive problem, putting it all together with this graphical stem. And this will have serve as a really nice warm up before Brian goes into BC1 for us. So what we have here in BC0 is a function f defined on the closed interval -312. And the graph of f shown in the figure above consists of 3 line segments and a semicircle centered at 10, 0. G is going to be defined as the function, the integration from 4 to x of f of t. On the time interval 0 to 12 seconds, a particle moves along the horizontal axis. At time t, the velocity v of the particle can be modeled by v of t equal f of t, where f is given in the figure above. V of t is measured in meters per second. T is measured in seconds. It's enough information for us to do a lot of damage with this question. So for part A, the question is the speed of the particle increasing or decreasing at time 5? Give a reason for your answer. Now, we had a good conversation, I think a couple of weeks ago, about particle motion, how to tell if a speed increases or if a speed decreases. Also, that can be reworded as, is the particle speeding up or slowing down? And that's all tied to the signs of the velocity and the acceleration. So in this particular case, we want to kind of recap the idea that v of t is equal to f of t. You don't have to rewrite that. You never are obligated to rewrite anything that's in the stem of the problem. But I'm going to do that just for organizational purposes, because I want to look specifically at what's going on with time 5. So what is the velocity at time 5? Well, we'll tell you. It's whatever the function value is at time 5, and that's something that we can interpret. So remember, this is a graph of f. I'll remind you there by scrolling. And f of 5 happens to be this y value here, right? This f of x value of -1. So we definitely have a velocity that's negative, which if we were to interpret that, I guess, that means that this particle was moving to the left at time 5. Now, what we want to do is kind of look at this idea of acceleration. And we do know that acceleration is the derivative of velocity, or more helpful to us in this problem, the derivative of the function f. So if we were going to take a look at a of 5, what's the acceleration at that same time? All we need to do is analyze what's going on with this graph at this graph's derivative maybe at time 5. So we look at the graph, here's our time 5, there's our point. Yep, that was the y value -1, but now we're looking at the derivative of the graph, and the way to take the derivative of a graph is to think about what is the slope of the tangent line there. And because we have a graph that's linear in and of itself, that means the slope of the tangent line is the slope of that linear segment. So we end up with a slope of down 1 over 1 unit. We therefore have the same value, -1. Now that's kind of interesting here. So we got to be kind of careful with our justification. So what we're going to say here is the speed of the particle, kind of doing that nut thing again, right? The speed of the particle kind of acts as our noun, but we have more information to write about that, right? We want to make sure we answer, is this increasing or decreasing? So we're going to say is increasing. We want to address our time. So let's say that the speed of the particle is increasing at time t = 5. And I believe that we do have a units in here, seconds. And the reason that we know the speed is increasing is because v of 5 and a of 5 are, well, I guess there's a variety of ways that we can say this, but the way that I would prefer is to mention the fact that they both have the same sign. V of 5 and A of 5 are both negative in this case. It's just ironic that they are the same value. And I wanted to stay away from that a little bit to say, oh, they have the same value. Well, that's certainly going to mean that they have the same sign. I don't want to get you confused by the fact that we're really looking at what the signs are. That's kind of the important idea that's going on with this particular justification. Okay. If we look at part B, same stem, of course, asks us to find the definite integral from 0 to 12 of the absolute value of v of t with respect to t, use correct units, interpret what that means in the context of the problem. So first of all, let's go ahead and evaluate this definite integral. And we have to remember that our good friend v of t is denoted by the graph of f of t. Well, now looking at this absolute value of this f of t graph, so these portions that we see kind of down here below the x-axis, if you want, you could resketch them if it's easy for you to do, if it's easy for you to think about. You can picture those kind of being out above the x-axis or the t-axis. And I suppose we could do the same thing over here, but I don't think that's going to come into play, as we are only interested in finding out what's happening between 0 and 12. So we're going to take the areas of essentially these three separate regions here, 1, 2, and 3, I may call them. And as we do that, we are going to use our wonderful friend geometry, because we have this wonderfully behaved graph that behaves according to some nice geometric area formulas. And so the area of our first triangle shape has a base of 4, a height of 4. So we have 1/2 4 times 4. To that, we shall add another area of this triangle here, region 2, which is now positive, sitting out above that x or t axis. And we have a base of 1, 2, 3, 4, and a height of 2. And then finally, we have a semicircle whose area is 1/2 pi times the radius squared. And we can see that the radius is certainly going to be 2 in that case. So if we simplify this, we would end up with 8 plus 4 plus 2 pi. It didn't take terribly long to simplify that. If you feel like it's going to take a while to simplify, don't worry about it. You can leave your answer as an unsimplified numeric value and still receive full credit. Now we want to interpret the meaning, and this is going to draw upon some previous knowledge that we talked about probably more than once during our mornings together. And that is, when you integrate the absolute value of velocity, you get the total distance traveled. Remember, if you integrate just the velocity, you get something called displacement, which doesn't account so much for moving forward and backwards. But when you integrate the absolute value, we're kind of thinking about integrating or finding this this distance all in one direction, so to speak. So we're just simply going to say that the integration from 0 to 12 of the absolute value of v of t represents or is the total distance. We like that word total. It's very descriptive. The total distance the particle travels. And I'd say that we have a label here to probably throw into the mix, and that would be in meters. And so right now we're doing a pretty good job. We've got na, right? We just need the t, right? We need the time. And remember, this is on an interval. We're explaining the meaning of an integral, so we need an interval. And so we'll say from time t equals 0 seconds to t equal 12 seconds. And there's your total distance traveled. Justification, interpretation. All right, let's move on to part C, last part for this one. Using correct units, let's explain the meaning of 1/7 times the integration of 1 to 8 of v of t in the context of the problem. Once again, you're using an idea that appears sort of within that integration unit that you had spent quite time on in the class. And you have to recognize the fact that this is that thing that kind of looks like this in most textbooks, 1 over b minus a times the antiderivative from a to b of some function, let's say. And we hope that you all recognize that as the average value of the function with that name, right? That's just a generic name, f of x. We have the exact same thing going on here. We're going to be looking at this as the average value of this function that now has a contextual name. It has a contextual meaning, velocity. So we'll just simply say that this is the average, we can abbreviate, velocity, the average velocity. If you want to get a little bit more descriptive, you could say of the particle, the average velocity of the particle, and we do need units, and we'll say that would be in meters per second, right? Meters per second. The reason is our velocity is already meters per second. When we multiply that by another time seconds, the seconds cancel, so we only get meters right here. But then, of course, when we divide by this 7 time interval, that gives us another seconds denominator. And of course, we want to use some kind of a preposition over from so that we get the time interval. So over the interval, we'll say, we use a little bit of a different way to phrase this. Over the interval t equals 0 or t equal 1, sorry, seconds to t equal 8 seconds. All right, so there's a nice cohesive velocity particle motion problem that could very likely mimic some of the things that you're going to see on your AP exam, because remember, you will not see parametric motion on this year's particular exam. So Brian, you are going to take BC1 and get us starting. The shark fin problem, I love it.
Yes, let's take a look at BC1. And I love how Tony explained that last example. And I want students to make sure, like, we have to be careful because, Tony, I'm not sure how your kids do with this, but my students, I think they're pretty typical for students. I mean, obviously my students are better than everybody else's students because everybody's students are better than everybody else's students, right? Because we get to see them every day. But in my classes, sometimes we have some confusion between average value versus average rate of change. And we know that average value is that integration concept that you showed us, and the average rate of change, we might call it AROC, is the slope between 2 points. And when the questions go ahead and just use that terminology, if they say find the average value or find the average rate of change, there's not a lot of confusion, because just remembering which formula it is, because they're telling you what to do in the problem. But then problems like you just shared, Tony, where they don't mention the phrase, or in wording, they might have just said find the average velocity, right? They wouldn't have said find the average value of velocity. So when they see that word average, they're going to they say, hey, what's the average velocity? Students are going to have to recognize in context which one of those two formulas to use. So we want to make sure that we understand the differences between those two things and when to use each one. So and Tony did a really, really nice job recognizing that. And Tony, I'm sure you're the same way, but if we see a definite integral on the exam and there's that fraction in front of it, a 1 over something, it's not guaranteed. But when you see that, to me, it's always like Tony draws these thought bubbles, right, for his students. It helps them think, okay, what I'm thinking. For me, I tell my students, like, bells go off. Like when I see that 1/7 in front, I'm automatically thinking, okay, this is probably an average value theorem. Let me think if it really is really going to follow through with that. So it's a really good way to kind of keep that on your mind. So BC1, we have 2 full FRQs on today's file. So we're going to go through BC1 today, Tony and I are, and then we're going to leave BC2 for you. But I want to take note of these 2 FRQs because we wrote these yesterday just for you, and they're meant to mirror the first problem on this year's exam, right? So we know this year's exam, problem number 1 is a 25-minute question. Trevor Packer has done a couple webinars with teachers and other people, and he's mentioned how the first question is 25 minutes. They want to keep you busy. They want to give you lots of opportunities to show what you know. And so he said a lot of students may not be able to get through all of the parts. They may have more parts in the problem than you can do. So we want to kind of warn you now. Don't be overwhelmed if you get to BC1 even next week and we put a timer on for you and you've only gotten through 5 of the parts before your timer goes off, right? Don't keep working and try to push your luck and hope that you can get uploaded in time. It's okay. He said, if you don't get through one of the parts, you can still get a 5, right? But they want to give you lots of opportunities with only 2 questions to show what you know. And so the only way to do that is to give you a lot of problems. So these 2 problems are our interpretation. This is not from the College Board. It's not official. We don't have any insider information, but we write these problems for our own students to give them some practice about what this might look like, right, this year. So it might just give you an idea of the kind of things they might put you through. So it is a BC exam, a lot of AB material. And so this is why we're calling it putting it all together. So here's our first response problem of the day. So we have a table of values. Obviously, you can see here we got F and F prime. And then we have a graph of G. And it says in the problem that G is 2 line segments here and then 2 quarter circles, doing it right, a little shark there. And I think Tony was wanting to start this problem originally because he always loves to incorporate little sounds and things like that into his sessions. I'm sure he would have been singing the Jaws theme song over there. But we got this information and we're told that F is twice differentiable. So part A, is there a time between -1 and 7 such that F prime of C equals -1/2 and justify your answer? So right off the bat, right, when you start seeing questions that start asking questions about like, must there be, is there, can you guarantee, explain why there must be, right? We call those existence theorems because it's just, how can you know something exists? How can you be sure it's out there? Even if you can't find out where or when, how do you know it must be true, right? And so when you see those, your first thought, right? I'm going to do a Tony right here. This is my first time ever doing this. I don't even know how to do it the right way. So Tony, I'm sure will grade me afterwards. But when I'm thinking about something like that, my warning bells tell me this is probably going to be an MVT or an IVT question, right? And so I always tell my students, as soon as you see that wording, write down IVT, MVT above it, because that at least gives you a starting point. It tells you what you're looking for, right? And then next step, let's make a decision on which one it is. And yesterday in one of our problems, we did one like this, and I made a comment that the way you can tell is look at what they're asking about, right? What are they asking about in the problem? And then look at what you're given in the problem, right? If they're asking about the same function you were given, that's an intermediate value theorem. Intermediate value theorem talks about points on a graph, right? And so they would match. Whereas the mean value theorem talks about a derivative of a graph. And so you would ask yourself, is this the function that was given, or is this the derivative of the function that was given? Well, yesterday we did a nice job. And so I thought I'd throw a little bit more of a twist today because guess what? We're given both functions. So in theory, on the surface, we could think about this as IVT or MVT, right? If it was going to be IVT, we would be looking at F prime, because if the function they're asking about is what's given, the same function, F prime, that would be an IVT question. And IVT talks about points. And so we're looking to see if this value is somewhere between the values in the table with IVT. Well, unfortunately, -1/2 is not between any of those intervals. So IVT in this case actually would not work, right, with the F prime graph itself. So we're gonna kind of maybe hopefully look for an MVT method, right? And so for MVT, it's pretty straightforward. Once we know what's going to be MVT, the first step is let's go ahead and plug in those values into the function that we're going to be checking, right, for MVT. And so we're going to be using f of x. So we're going to go ahead and write on the paper, right? Remember, we're always telling a story with our work. So even though you might be able to do a lot of this in your head, you really have to tell your story when you're doing an AP problem on the free response. That way we can see what you're thinking every step of the way. So f of -1, we go to the table, that's just going to be -2. And then f of 7, the other endpoint, if we go to our table, that's going to be -6. And what I like about this method of first realizing the question means it's probably going to be IVT, MVT, and then making a decision is the first step wouldn't change whether you were doing IVT or MVT. The first step I have my students do, either method, is take the two endpoints and plug them into the function, right? It's always the same starting point. The second step is, what do you do with those numbers, right? If it was an IVT problem, you would just show that the value you're looking for is between those two numbers. If it's MVT, we're talking about derivatives. It guarantees a instantaneous rate of change. So we're going to take the slope of those two numbers. So -6 over -2 equals 7 minus -1. I don't think I did that correctly, Tony. Am I on the right track here? Negative f of -1 is what? -2. And then f of 7 is -6. And as I'm working through this, I am not seeing, this is going to be what? What is that? -4 over 8? Oh yeah, double negative
Got it.
signs, right? This is a good example of why you should use a calculator. My brain was seeing a minus and -2, and I was completely ignoring that, right? I kept thinking I was going to get -8 on top, but it definitely is +4. I wrote this question, and I almost missed my own question. So -4 over 8, hey, guess what that equals? That's -1/2, right? This is the average rate of change. And the mean value theorem says, if you find the average rate of change, the derivative of that function, f, will equal that somewhere under certain conditions, right? So the good news is those things match, which they're going to have to for mean value theorem. And then as long as we've met our conditions, well, our conditions are the function that we're using, f of x, has to be continuous and differentiable. Well, is it? Well, the problem says that f is twice differentiable, so we know it's differentiable. Do we know it's continuous? Of course we do, because if a function is differentiable, it must be continuous. We had a theorem that says that earlier in the year. So once we know that, we're now going to go to our conclusion, and we're going to say, since, what was our function? It was f of x. Since f of x is continuous, notice we have to say it's continuous with mean value theorem. I know that differentiable implies, it means it must be continuous, right? That's a theorem, but as a reader, when we're grading your papers, we don't know if you know that or not. We don't know what theorems you know and don't know. So you have to state that, right? Sometimes students and teachers will say, well, why do I have to state that when we know it's true? Well, that's why you have to state it. You have to tell us that you know it's true. So since f of x is continuous and differentiable on, what was that interval? That was -1 to 7. The mean value theorem guarantees, we got to use the mean value theorem. If you call this IVT, you won't earn the full point because we're using the wrong theorem. Guarantees, and yesterday we said, let's just repeat the question. Once we get to here, we're just going to repeat the exact question in their own words. So there is a time C. So I just repeat it word for word. I don't even change a single part of it because that means I know I'm not going to missay something, such that f prime of C equals -1/2. And that's what we mean by justify. Justify means use a theorem or a definition properly. So showing the average rate of change and then using our conditions or conclusion will be how we justify that. Moving on to part B of this problem, same two graphs, right? Part B. says let h, we introduced a new function h, be g of f of x, a nice composition here. Find h prime of 5. Well, chain rule is essential, right? I think of the big rule with derivatives as chain rule. The big rule with integration is u substitution. The College Board is certainly going to want to know that you can do those two things. But they just ask a normal problem, like from a textbook or something. They know you might be able to look it up on a book. You would probably Google it. You could probably use a photo math app or have a CAS calculator, right? You could just type it in and get an answer. So they're not interested if you can just look something up or use a calculator. They want to know, do you understand the rule? And with the take-home test, these are the kind of problems that we can still test you on, right? Because you can't CAS your way to the problem like this. And so we want to find h prime of 5, h is derivative. And so we're going to go ahead and differentiate both sides with x first before we start plugging numbers in. And chain rule, we take the outside's derivative. So g becomes g prime of f of x. And then by the chain rule, right, we have to multiply by the inside's derivative, f prime of x. And once we have this, it's really just plugging in some values and then making sure that we know how to find these values with the given information. So understanding compositions and understanding the order we're going to do these things in, we have to find f of 5. Well, fortunately, we have a nice table. So we have g prime of -1 times f prime of 5. And now to find g prime, I'm going to go over here. This is a graph of g. So g prime would be the derivative. Well, it's a slope in this case. We're at -1. So we're looking right here on the graph. And I put this point here on purpose because sometimes students have a hard time when the point is given and they want to like try to find the slope. Because what my students do sometimes is they get kind of overwhelmed and they'll try to like figure out the slope of that little part right there, right? But that may be a little bit short-sighted because this point is part of a linear segment, right? So don't worry about where that point is exactly. If your point is on a linear segment, the derivative right here is the slope of the entire line. So it's easier sometimes just to go ahead and think about the entire line segment and find the slope of the entire segment. Whatever this entire segment slope is going to be the derivative because a linear function has a constant slope. And so g prime of -1, well, this blue segment, the whole thing where this point is at, has a slope of down 2 over 4. So it's going to have a -1/2 slope. And then we want to also figure out f prime of 5. Well, we have a table for that. We're going to go to the other value. So it's going to be times 3. And our final answer is -3/2. Right, so two nice conceptual problems that will get us started off today. So part C of this problem, I just mentioned the College Board certainly is going to want you to show that you can do chain rule. And also they want to see that A, you could use U substitution or integration, as well as some fundamental theorem of calculus. This is another nice example where we can test those ideas. If you're familiar with your calculators, you realize you can take a definite integral on your calculator, right? You can just do like your Math 9 if you're a TI person, or if you're an Inspire person, you can ask Tony how to do it because I always forget how to do the Inspires. But there's easy ways in the calculator. Well, again, we're not as concerned about calculator work right now. We want to know, do you understand calculus? And so we're going to write some questions that are still testing the same ideas, but will eliminate a lot of those technology aspects. So here we're integrating from -1 to 1 of f prime of 5 minus 2x plus 3. And every time we are integrating and you see kind of like those parentheses, that's sort of a warning bell that you're going to be using U substitution. But we're going to have this plus 3 also. So I think the best way maybe to start this problem, just to avoid, whenever I'm doing U substitution, sometimes what happens is a part of the problem will need U substitution, but the other part doesn't. Or maybe the two parts both use U substitution, but they're different types of substitution, like different U values, right? When that happens, leaving it all as one integral can really cause some problems because you have this constant in front and maybe it's applied to the whole thing or it's not applied to the whole thing. And so we want to be really careful how we address this. And so here, I think the best way to solve this is just to break this up using some of our properties of integration that you can split up a sum of integrals as long as they're both convergent. And then treat these separately. And I'm going to go ahead and fix this right here because we're not going to add that twice. See, I'm catching all my mistakes already. It's amazing how smart you are when you're not on live television and you're not talking while you're working. Once you get on live television, it's amazing how many mistakes you might make. So this first part here, we're going to use some u substitution. And so I'm going to immediately put whatever's in parentheses. The 5 minus 2x is going to be our u value. And then find du. Well, our du is going to be negative 2 dx. And again, we mentioned this yesterday. A lot of teachers teach us different ways to do u substitution. And if you learn a different method and you're good with that, then just do it, right? There's valid approaches on a lot of different approaches. So this is just how I like to teach my kids to do it. And then we say, once we have our du figured out, we want to make sure the problem has that exact du. I want this to match my u and du. So I'm kind of missing this 2x. And so the beauty of integration is, one of our properties is you can multiply by a constant as long as you offset that constant in front. So I can multiply by a negative 2 to get my du there, and then multiply by negative 1/2 in front, because negative 1/2 times negative 2 is 1. So really, I didn't change the value of this problem. I just used a weird looking 1. And then I'm going to rewrite this as negative 1/2 of f prime of u times du. So I always rewrite it in terms of u. I didn't include the limits yet, because remember, those were x values. They weren't u values. And so we're going to, if we do u substitution, I can't put a negative 1 and a 1 there, because now we're actually making a false statement. We've written something down that's not correct. And so you're always in putting points in peril, is what sometimes they call it at the AP reading, meaning you had some good points, but now you're risking it, right? And so we want to make sure that we don't call that negative 1 and 1. We're going to convert everything to u values, but that's why we have our conversion here. U is always 5 minus 2x. And so if I plug in negative 1 for x, we're going to get 7 for our lower limit. If I plug in 1 for x, we're going to get 3 for our upper limit. And I know those are kind of in the wrong order, right? And so we have the option to flip them, reverse them by making the integrand opposite, right? And so if I do that, we're going to make this a 1/2 times the integral from 3 to 7 of f prime of u du. And now all I have to do is use my fundamental theorem of calculus on this part, right? So the fundamental theorem of calculus says the integral of f prime is just f of u from 3 to 7, which means this part of the integral is going to be 1/2 times the quantity f of 7 minus f of 3. And we can go to our table of values and pull those values out. F of 7 is negative 6 and f of 3 is 2. And then working this out, this becomes negative 4, right? Negative 6 minus 2 divided by 2 is negative 4. That's not our final answer, though. That's only this first part. I also want to make sure I integrate this negative 1 to 1 of 3. And we could use the fundamental theorem of calculus. The integral of 3 is 3x. And then from negative 1 to 1, notice I'm using negative 1 to 1 here because I didn't use u substitution on that part. I left things in terms of x with the dx there. That's going to be 3 minus a negative 3, which is 6. And so the sum of all of this, right, when I broke them up, my final answer is going to be negative 4 plus 6, or 2 is my final answer. So a lot going on in that problem: u sub, fundamental theorem, some integration properties as well. The last part that I want to show you, notice part A, B, C, those were all A-B questions, right? Because a big part of the BC curriculum is still going to be A-B topics. Part D is normally an A-B problem, but for this year, it's a BC question because it comes from that Unit 8 from the College Board curriculum, average values. We mentioned that before, right? But that's a Unit 8 idea, so it's kind of a BC, honorary BC question this year. And then when we're finished with this, Tony's going to lead us into 2 more parts that are going to be BC only. So the average value of G. So before we start trying to solve things and do things, it's always good to just interpret this. If you don't have a mathematical equation or a mathematical thing they're asking you to do symbolically, it helps to write that out before you start looking at the graph or information. So how would you find the average value of something? Well, Tony just mentioned it, right? If you had a bunch of test scores in class, you have all these test scores, and I say, hey, what's your average test score? Or what's the average test score in my class? Well, what would you do? Wouldn't you add up everybody's scores and then divide by how many there were, right? That's how you find an average of something. You add them all up and divide. That's what we're going to do. The difference is it's not discrete. It's going to be, infinitely small pieces that we're adding up. And so, but we still have to add things up. So we want to find the average of G. So we have to add up all the G's and then divide. Well, how do we add up in calculus? Well, in calculus, to add things up, you integrate it, right? So if we integrate or add up all the G's from -4 to 5, that would add them all up. And to find the average, we have to divide by how many or how long it took. Well, from -4 to 5 has a span of 9. Here's where that fraction comes in. So now that I know what it wants, it's just going to be 1/9 times the integral of G from -4 to 5. And we're given a graph of G. So in this case, we're not going to use the fundamental theorem because we're not going to actually integrate G because we don't know what G's antiderivative is, a capital G, but I can't have any information that will help me do that, right? So I don't want to use the fundamental theorem here. We want to make the connection that the integral of a function, the definite integral, is the same idea as finding the signed area. So in this case, it's just finding all of this, right? So the integral of G is just the net area of those two shapes. And so in blue, it's below the x-axis. So it's going to be a negative area, or it's a positive area, but signed area is negative. It's below. It's a triangle shape, so we can do -1/2 base times height, and the base from here to here, might not be able to see those numbers. This is -4, and that's a 1. So the base of that triangle is 5, and the height of this triangle is 2. You don't have to call that a -2 because I already put my negative in front, right? So putting the negative out in front took care of the fact that the height was going down to -2. That's the area of the triangle. And then this red piece here is a little bit trickier. So I'm gonna break this up because it's 2 quarter circles, and the first quarter circle kind of ends right here, right? This is kind of the first piece. And then the second piece is this little shape, this little doodad right there, right? And so we're gonna have to add those two pieces up. The first part in red is a little bit simpler because it's just this quarter circle, right? 1/4 pi r squared, and r is 2 in this case. But the green shape, that's not, it's connected to a quarter circle, right? But it's not the quarter circle. If I did 1/2 pi r squared again, I would be finding kind of this part right here, right? This would be 1/2 pi or 1/4 pi r squared. I don't want that piece. I want the underneath part. So what we're going to do to come up with that is let's figure out the entire square here, right? So that's going to be, let's add the whole square, which is going to be just base times height. But then I don't want the whole square. Let's subtract the part that we don't want, right? I don't really want that part of the square. So this is the quarter circle. So we're going to do this whole square minus this part that I kind of colored in black here, which is going to be a fourth of a circle, 1/4 pi r squared again, like that. And that will give us sort of the piece that we want. And guess what? We don't have to simplify this, right? We don't have to reduce numerical answers. And I would recommend that you don't because of mistakes that you could make, as well as timing on the exam. So this would be my final answer. Remember, we have that 1/9 in front. We don't want to forget that because it was average value. We weren't just adding them up. We were adding them up and then dividing by the span. So that's going to be our average value of G from -4 to 5. So that was our kind of our transition. AB was parts A, B, C. Part D was kind of a BC only topic this year. And then Tony's going to bring us home with a couple of more parts at the end that are BC only.
Yes, indeed. So taking a look at the BC only topics here, part E, very short question, just asking you to integrate x times f double prime of x from 1 to 7. And so often, whenever we are integrating a product to things, it sort of puts us in this decision-making mode because it's very likely that you're either going to use a U substitution, which is an AB idea, or you may be slipping into this integration by parts mode. And the way that you can make that decision, you can answer that very, very quickly by just addressing the fact, now, if you were to let a part of this be your U substitution with the idea that you were going to take the derivative of that U, we have to realize that that derivative has to match another part of the integrand. And quite often that U substitution you make is the variable that's located, or the value, I should say, that's located in parentheses. And we see that there's just no way of making a U substitution happen, right? Typically, in a given year, when you're multiplying two pieces together in an integrand, and one of the pieces is what we call transcendental, which is the math version of just weird, right? Sine, cosine, natural log, e to the x, then that's a dead giveaway that you're probably going to use integration by parts, but you may not have that luxury this year because of a lot of the functions being disguised, like this one, f double prime of x. So we're going to go with with an integration by parts approach here, and I will set this up as I normally do: u equal and dv equal. But again, use whatever organizational structure that works for you, and that would include setting up a table using the tabular method. We want to let u be x in this case because we know that that derivative will kind of dissipate eventually. But more importantly, we want this integration dv process to be operated upon f double prime. And the reason is because it will twist that f double prime around a bit and turn it into an f prime. And I see some information in the stem of the problem that deals with f prime. So if we take our derivative moving down, du would equal dx, of course. And if we take our integral moving up, v du would equal dx. How about that? And if we integrate moving up, v is going to be f single prime of x. And now we just assemble our formula for integration by parts, which says u times v, so that's x times f prime of x. And again, you could depart from the definite integral environment as long as you put it all back together. Now that's a little precarious because sometimes we forget that this was a definite integral. So if you want to remind yourself that we need boundaries, you could use your normal sort of such that notation that we need to plug in a 7 and a 1 and subtract. And then we subtract what is going to be another integration expression, right? V times du will be housed in this another integral, f prime of x dx. And of course, our boundaries are still 1 to 7. Now, got a little bit of work here still to do on this integration, so I'll just drop this x f prime of x down. And as I integrate f prime, that's a pretty easy thing to deal with because the integral and the prime mark essentially cancel each other out. And now I have this expression that I can evaluate from 7 to 1 as such. We need to evaluate before we could earn credit, of course, so we plug in our 7, looks something like this. And then we subtract quantity, and next we'll plug in our 1. 1 times f prime of 1 minus f of 1, it looks like. Be really careful. Make sure you have some grouping symbols around this expression because it is a multi-term expression that follows a minus sign. We still would not earn full credit because we always have to extract values from the table and write this as a numerical expression. So our f prime of 7, as you can see, can be read from the table. F prime of 7 is 4, and our f of 7 can be read from the table. Just make sure that we read the correct rows. We don't have to worry about doing any simplifying here. F prime of 1 is going to be positive 1, and then f of 1 looks like it's going to be a negative 2. And we're going to stop right there because if you were to add all this together, hopefully, I think it gives you a 36, but that's going to be perfectly acceptable to leave your final answer. Okay, so let's move on to the last part, which is, oh, what's a great FRQ without something to do with the Taylor polynomial? So we're going to define k of x to be this integration, this expression with an integral, 3x plus the integration, negative 2 to 2x of g of t. And our job is to write the second degree Taylor polynomial for k about x equal negative 1. It's just the way that we come up with these coefficients. It's going to be very it's a clever use of the information that's given in the stem, putting it all together. So again, we know that our general framework, let's say, for our second degree Taylor polynomial will always look like k of what we're centered at or where we're centered, negative 1, add to that k prime of where we're centered. Now we're going to multiply by x minus where we're centered, which in this case is x plus 1, to the first over 1. And then we finish up with a k double prime of negative 1 times our x plus 1 to the second, all over 2 or 2 factorial, they're the same. So it's going to be very important that we understand what our values of k prime, and k double prime, and negative 1 are. So a lot of times I like to do this. I like to list what the generic functions are, k of x, k prime of x, and k double prime. Well, I'm not going to rewrite k of x because it's right here before my eyes. I'm just going to remember that. But I know that my k prime of x is going to involve taking this derivative. It's a little tricky derivative. Need to be careful here. The derivative of 3x is 3. add to that, and now we're back to our fundamental theorem, or one of our fundamental theorems, that say as long as we have this constant in the denominator, we can plop that 2x in as the replacement for t. But because this 2x is a little bit more robust than just an x, we need to take his derivative, which in this case would be a 2. And then below him, I'm going to go ahead and figure out what our value of k double prime of x is, our expression, and the derivative of 3, of course, is going to go away. And in this case, I would take the derivative of g of 2x times 2, which I can see that this 2 constant is just going to come in front. The derivative of g of 2x is g prime of 2x, but if I multiply by another derivative of 2x, which is a 2, those 2's would multiply to give me 4. G prime of 2x. Now I think I can pretty easily find these values. Be nice if I use a different color here. K of -1. Well, K of -1 is what we get if we plug in -1 for x. And I might have to do a little bit of thinking here. This might be the trickiest of the one, so I'm going to use this space here. If x is -1, I end up with an expression that looks a little something like, oh, I want to say it looks a little something like this, which hopefully gives us the idea that this integration here with the same upper and lower boundary is just going to turn into a 0. So k of -1 is going to be -3. And then for a k of -2, let's use a little space right here. K prime of -1 next would be 3 plus 2 times g of something. Well, 2 times -1 is -2. And to read g of -2, we need to go to the graph. G of -2 over here gives me a x value, or a y value, I should say, of -1. Oh, darn it, I didn't get to use the shark fin on that one. So I have 3 plus 2 times -1, which is indeed +1. And then finally, for k double prime of -1, we're going to be evaluating 4 times g prime of -2. Now that -2 value is still kind of on my mind, but as Brian said earlier, we're going to talk about taking the slope of this, and we want to really think about going from point to really make sure you get a very reliable slope there. And I think we have -1/2 in this case. And of course, 4 times -1/2 would be a -2. Now, put it all together, assemble your furniture, and you have your k of -1, which is -3. K prime of -1 was +1. And you got to be kind of careful here. By the way, you could put these in parentheses. It is kind of nice to have them sort of organized that way. And then for our last term, got to be careful here, because the k double prime we said was -2. We still have to remember to divide by that 2, or that 2 factorial. So that would be a -1 quantity x plus 1 squared. And there's your result for part F. Brian and I had debated, oh gosh, BC1 or BC2, they're both amazing questions. We really didn't know how to make the call. We really want you to look at BC2. We'll feel bad. Brian did a really good job of assembling the framework here of BC2. It's got some great parts to it. And then of course, you've got a couple of wonderful parts or questions with a form of BC3 and I think BC4 that surround yourselves with the whole convergence of series and the ideas that are associated with unit 10. And a lot of times that's kind of a trouble spot with some students. And so this is your chance to really practice a lot of those ideas with your BC3 and BC4 that you have on your document. All right. I think we can wrap things up, Ryan. What do you say?
Let's do it, Tony. And Tony, before I let you start tweets with Tony, I want to make one quick mention. On Monday, I mentioned that if we can get 50,000 views this week, right, for these 5 videos, Monday through Friday, I'm going to pie you in the face. And we realized the other day we were trying to do high fives in the wrong direction. We weren't doing a very good job. So I've been working behind the scenes on that. And we're not at 50,000 views yet, but it's because we know that a lot of students watch it live. A lot of students will watch it like later that day or the next day. And so it takes about 2 or 3 days for all the views to kind of catch up with the videos, because a lot of people are 1 or 2 days behind. So come Monday, that'll be our finally tally mark. And so just so you know, Tony, right now, we are kind of pacing, right? We're about 40, we're pacing for about 48,000 if I extrapolate the data. So students, get your friends. make sure they're watching these, not just because we want to pie Tony in the face, because this is really good practice for the exam. We want to make sure everyone is ready, doing these problems, getting more prepared for the exam. So on Monday, we'll do our final tally. If we get 50,000 live on the air, I want to be pieing Tony right in the face. So tweets with Tony today, what do we have?
All right, and I'm excited about that. I'm excited about that pie. All right, so AP teachers rock. I want to first of all give a shout out to our friend Chloe. Chloe, thanks for this tweet. She wants to shout out to the best calc teacher, Mrs. Henderson. Thanks for always being there for us and making calc fun. We miss you. Mrs. Henderson teaches at Legend High School in Parker, Colorado, just a suburb of Denver. Brian and I are a little sad. We were scheduled to go to Denver to do a training this summer in the beautiful town of Golden, and we won't have the opportunity to do that, at least live, but we will do it virtually. And Brian, I got a feeling that you and I probably will have some mountain backgrounds in our Zoom sessions, because the Denver is such a beautiful, Colorado is such a beautiful place. We also want to recognize another teacher shout out, because there's so many of them coming in, but it's a shout out to Mr. Malush at American High School. His dabs and pobs are great ways of teaching calc. This is possibly his last year teaching, so it'd be great to give him recognition, and we would certainly wish Mr. Malush a tremendous amount of success and well-being once he does leave. That's from a Fremont, California, American High School, which is in the Bay Area, San Francisco Bay Area. And then for our AP students rock, shout out to my AP Calc BC class, Fort Chester High School. This was my first year teaching the course. That's always tough. We know that. We've been there. And they helped me get through it, as well as working well together and sharing lots of laughs, mostly at my expense. Brian, I can always relate to that. That's for sure. And that is from a Mr. Raskin, I believe. Yes, Mr. Raskin from Port Chester High School. It's in Rye, New York, or the village of Rybrook, which is sort of, I think, east of White Plains, above the city, right? Kind of on the Connecticut border, I believe. So there are your tweets of the day. Brian, what you got?
Awesome. Don't forget, next week, we're going to be going over all the exam information. It's still there. Every day, we're going to be talking about logistics, the site, uploading, all that. You're going to have a chance to practice actually doing an FRQ. We're going to be putting out for you as well, a mock exam on Monday, Tuesday, Wednesday, Thursday. Yeah, a lot of opportunities to practice. So join us next week. And don't forget, next week on Tuesday, our good friend Steve Kokoska will be here. But on Monday, some time practice, uploading, strategies, debriefing, exam information. It'll be a really great session. So it'll be helpful. And then, as always, we end the day with our pets of the day. We got so many great pets today, and I want to do them some justice if possible. But we've got Belle, we've got Peyton and Moose, Astro and Sugar the cat, and then Bolt. A lot of great pets today, and all these pets are so awesome. I had to give them the Passwater approved stamp. Right, this is a Passwater approved stamp. Wonderful pets. Keep sending in your pets. Let us know how awesome your pets are. Let us know how awesome your students are, how awesome your teachers are. It'll be a great way to honor all of them. So looking forward to pieing Tony in the face on Monday. So I hope that you will get your classmates to come watch some of these videos, get prepared for the exam, and then come watch us live on Monday to see that happen. And as Tony mentioned earlier, check out that demo, right? If you need to go back to the beginning of the slideshow and find the College Board link, right? So you can practice over the weekend, just uploading the file, see how it's going to work. It was College Board cb.org/AP demo, but you can go back and see that slide. So as always, Tony, Anthony's going to take us out. Final thoughts.
Stay safe, guys. Keep learning.
AP Calc, yes, AP Calc. Welcome here to AP Calc, yes, AP Calc.